Today's going to be talking about adaptive tetrahedral meshing, personalized cardiac simulations.
Thank you. So I'd like to thank the organizers of this wonderful meeting for inviting me. And so I have the opportunity here to talk about some aspects which is important for building patient-specific cardiac models, which is the meshing. So I'd like first to acknowledge the people that have been involved in this work, especially Hans Lamaker, who has done most of this work, and in the framework of actually the UHeart project. We're interested here in patient-specific cardiac simulation. So this starts with patient-specific data, namely mostly images, from which we can actually do some image segmentation algorithms in order to extract the structures of interest. For instance, here, the right and the left ventricles. And from that, we need to translate this geometric information into a computational mesh. And this is an issue which is, I think, fairly still needs to be a lot of work needs to be done on that, and that I will tackle. So which type of computational mesh do we need? And this depends on the discretization method which has been chosen. So we have seen this morning, for instance, examples of simulation based on a meshless approach or boundary element models, which require only a surface mesh. But at INRIA, we base our simulation models on finite element models on actually tetrahedral elements, and in fact, actually linear tetrahedral elements. So in this context, why actually producing a good mesh is important. So actually a mesh is a way to sample a domain, a continuous domain. And so you need to be careful into the approximation you make by approximating this continuous field. And here, for instance, you can bound the error you make by approximating a continuous field into a linear tetrahedral elements. And this is depends on the maximum edge length of the tetrahedron, but also it depends on the second derivative of the function at that locations. So that means that if you want to decrease the error of interpolations, you need to have a small edge length, especially where you have a non-smooth field. So this is one first constraint you need to take into account, which is the interpolation accuracy related to your mesh. The second aspect, geometrical aspect of that meshing constraints is related to not only the field interpolations, but the gradient of that field. So for instance, in many cases, you're interested in not only computing the field, but its gradient. In mechanics, for instance, you compute the displacements, but you are also interested in the strain information, strain being related to the gradient of that field. And here you can also prove that the error you make in the gradient, approximation of the gradient, is bound also by the second derivative of the field, but this time not by the edge length, but the shape of the elements. And that means that if you want to have a good approximation of the gradients, you need at that locations to have a good, basically a tetrahedron which is as regular as possible, and especially you need to avoid the flat tetrahedra. And this is why people have come up with some metrics that measures how a tetrahedron differs from a regular tetrahedron. Now, this is for the geometrical aspect, but you have to take into account the physical aspect. For instance, if you are using fast marching methods for iconal models, if you want to have respect the causality of the information being propagated, you need to have a dihedral angle which is less than 90 degrees. Dihedral angle is the angles between two faces of your tetrahedron. And for isotropic diffusion, it has been shown that if you want to follow the maximal principles, you need to have this quantity here, which must be positive, okay, which also involves the dihedral angle and the length of the edge length. So finally, the numerical aspects, you want to the convergence of your numerical schemes to converge as fast as possible. And that means to have a low condition number. And this low condition number can also be, in the case of isotropic diffusions, can be related to the geometry of your mesh. you can show that you need a large tetrahedra. Large tetrahedra needs to be regular, so it's the large one that matters, and you need also homogeneous volume of tetrahedra as possible, as homogeneous as possible in your mesh. So this is just to show the importance of your of a meshing in geometry, physical, and numerical aspects. Now, adaptive meshing is a way actually to achieve a trade-off between the accuracy of your meshing, so having a good shape elements, and also to have efficient schemes by lowering the number of elements. So the two questions I will tackle in this very short presentation is what are the adaptation strategies are suitable for cardiac simulation, and the second one is what is the impact of this meshing on the simulation. So we have started to work on these adaptations recently and proposed this pipeline, starting with some output of segmentations, and then producing a surface mesh using some isosurface extractions, which can guarantee, for instance, the topology of a mesh. And then we use the sizing field, which I will discuss later on, and then first adapt the surface mesh and then produce the volumetric tetrahedral mesh. So I will start by talking about the sizing field. So the sizing field is basically when you prescribe the edge length at each point in space. So these sizing fields can be dependent on the shape of the structure. For instance, here we use the right and left ventricles. So we extract the skeleton using distance maps, and then we extract the thickness information at each point in the mesh, in the field, in the space, sorry. And then we use this function here in order to prescribe the number of elements in the myocardium, the septal, for instance, on the myocardium. So you can control the number of layers of elements if you want to take into account the heterogeneity between endocardium and epicardium, for instance. So this can be useful, and it will be demonstrated later on. You can also use boundary conditions as a way to produce your sizing fields. For instance, here we decide to take into account the location of the scars extracted from late enhancement MR, and in order to refine the mesh at these locations in order to better account for instance, re-entries in the ventricular tachycardia. So here the colors indicate that we have more smaller elements around the scars. But some also other groups have proposed to use the previous solution of a simulation as a way to guide the sizing field. For instance, this is a paper from Bella Madia, who recently produced, made an example where he refined the mesh around the propagation fronts of electrophysiology model. So this is an example where you have to remesh at its iterations. So our meshing pipeline, we have now a first extracted mesh, and we have a sizing fields, and we produce a refined surface. So this is what you see here. So on the left, you have an input surface mesh coming from the image segmentation. So this has a heart from patients with tetralogy of Fallot. You see the dilated heart, right ventricles due to regurgitation. So on the left is the input mesh, where you have a poor quality of a triangular mesh, and you have a sizing field. And on the right is the outcome of a surface remeshing, where you have good shaped element and where the meshing information, the sizing field, sorry, has been taken into account. So, and once we have the surface mesh, we can produce the volumetric mesh by filling it with a tetrahedra. So we can use different software which are available for that. Some of them are open source, and some of them are commercial. And so we started by doing some benchmarking of tetrahedral meshing software, but not taking into account the adaptive. So we use a non-adaptive feature. So you input is a surface mesh, the output is a volumetric mesh, tetrahedral mesh, without any sizing field. So for instance here, we compare the 5 different software, meshing the same surface mesh as inputs. And you can see some significant difference between, for instance, here. This is the mesh produced by NetGen. You can see that it produces only a single tetrahedron on the myocardium, while, for instance, this other software nicely have 3 different layers in this myocardium. And we have also compared some time of computation, quality of measures. And this is an example of on 4 different geometries. And well, you can see here the difference, high quality measures produced by some software. But as a whole, a good compromise, we found that the TEGEN software, which is open source, is a good candidate. And for the commercial software, we evaluated GSS3D as having a good, good properties. Now, I'm going back to the adaptive measures. So we have used here also the various software for producing adaptive thickness adapted measures. So we use the thickness of the myocardium in order to drive the edge length. And you can see that using this thickness measurements, you can easily control the amount of tetrahedra in the septum, for instance. So this is the range of edge lengths we use and the outcome of the measure. So you have here 8,000 tetrahedra. You can see that the myocardium here is meshed with only 1 layer of tetrahedron. And you can, so on, here you get 2 layers by just a scale factor. You can put here 3 layers, and it goes on like that, 4 and 5 layers. And of course, you increase the number of elements as you increase the number of thickness, tetrahedron in the thickness of the myocardium. Now, a question, of course, is what is the impact of that on the simulation? So here is some videos of a mechanical, electromechanical mesh, heart mesh. So the left one is using a coarse mesh with only 1 tetrahedron thickness, and the right one is a fine mesh with 3 tetrahedron thickness. And I don't know if you can see because they are not really synchronized, but the coarse mesh shows some excessive longitudinal motion and also limited torsion. But we have looked a bit more in details about the comparison of the different meshes. We could see, for instance, an impact on the PV loop of pressure volume outcome of this simulation. And we could see that we get, for the left ventricles, which is on your left-hand side of these slides, you can see that for 1 layer mesh gives poor results, but you get very stable outcome for meshes which have more than 2 layers. For the right ventricle, this is not as true, and the impact is not as important. But this probably means that if you are, depends on the objective, of course, of your simulations, but if you want to have some reasonable PV curves, you need to, a 2-layer mesh is probably sufficient for that aim. Now I will switch to the second examples, which is where the remeshing is based on the boundary conditions. So again, we have taken into account the location of scars in order to refine the mesh, and then we have produced this kind of mesh, which has actually 500,000 elements. And if I can zoom in the interested parts here, you can see the range. Sorry. The variation of tetrahedral size between the scars and the other parts of a myocardium. So now we have used those 2 meshes and I'm trying to compare the effect of the different meshes, the different adaptation for simulating electrophysiology in a case of a patient with the scars. And we were interested in simulating the VT stim, so a procedure to test the induction of ventricular tachycardia. And so now this is a kind of game. If you can see the difference between the 2 simulations. So this is the uniform meshing with only 44,000 tetrahedra. And on the right-hand side is 600,000 tetrahedra. So I'll let you try to guess what are the difference. Of course, I know the solution. So actually, the solution of that is you have these are the isochrones of a simulation. And you can see that you have the wave coincidence. So you have the waves are breaking and then they meet again. They differ significantly the locations of those 2 waves here. And you can see from the scars how they are located is that by refining the mesh, we were able to take into account the second isthmus, which is also of high importance for the VT simulation. So you can see the importance of adapting the mesh to the question you try to answer. And I think, and this will conclude my talks, there is a need for automatic adaptive pathology-driven meshing, because if we want to deliver tools for the clinicians to solve clinical problems, we need to automate as much as possible this transition from image segmentation to computational meshes. And there's still, I think, some work to do on this stage to really be able to automatically produce those mesh, which are also driven by the nature of the pathology. Another also point I'd like to make is that the meshing technique is also improving. Now we have the ability to use multi-label, and this is important. For instance, in the scars, you will be able to soon to have meshes where the boundary between two different structures are well followed by the mesher. And finally, because of course the anisotropic behavior of the myocardium, we could also try to use anisotropic meshing in the myocardium in order to take more into account the anisotropy of the fiber orientation. And finally, I'd like also to mention that the different meshes produced that I've shown here will be also transferred in the database that Nick is working on the UHeart project. Thank you.
So this is going to be a hot topic, I can see already. We have to speed on fast. So let's start with Alan, and then we'll have Gernot, and then we'll see how close we are to coffee.
Okay, we've seen a bunch of coarse meshes here today.
Right.
My understanding of electrophysiological modeling, given the very sharp DVDT that you have and essentially the shock front that the cardiac wave produces, there is a number, 0.15 millimeters. That is your maximum step size for stability. I don't know any. Yeah, and I'm pushing it, If you said 0.1, I would not argue with it. I don't know of any method that enables you to escape that criterion, and therefore any mesh that has elements larger than 0.1 millimeters is wrong. Is going to produce artifactual results in electrical wave propagation.
Well,
so, please, anybody.
Gernot developed our meshes, so it's, yeah.
So I think what they're doing is they're using phenomenological models that have a very flat upstroke. So in a physiological model, the upstroke lasts 1 millisecond, which translates into 1 millimeter in space. And you have to subsample that, so you have to go down to 500 micrometers, 250 micrometers. So, but if you use a phenomenological model that has a very flat upstroke, you get away with coarser meshes. So you cannot, on his meshes, you cannot run any physiological simulation. You can only do AF Banfield, Fitio-Nagumo with extremely flat upstrokes.
Which are not correct.
Well, depends on
the speaker participated in
Yeah, okay. So your point is, as I mentioned, the mesh must be related to the sampling thing. If you have a very steep signals, as you mentioned, you, as I said, this is related to the second derivatives, and therefore you need to. Okay, it's true, but now there is application, application-driven, incentive in the meshing. So here we have made some tests using a single bar, where we have seen on single bar the effect of the refinement of this electrophysiology model, the phenomenological model. That's correct, and to see if we have at some point the effect of the resolution on the conduction velocity and the isochrones. Because remember that we will compare those meshes, the isochrone of those meshes, with the clinical measurements. Okay, that's what we are interested in. We are not interested in the very detailed nature of the action potential. You see what I mean? We are interested in the time at which the fronts reach a given point.
I'm going to perhaps stop the conversation at the explanation. We have coffee, and I'm sure we can translate this.